Hi, welcome back. Today we want to look at how we verify Charles's law using the kinetic theory formula. So we first begin by stating Charles's law. In brief, it tells us that the volume of a fixed mass of a gas at constant pressure is directly proportional to its absolute temperature. So V mathematically is proportional to T. If we remove the proportionality constant and introduce the equal sign, you do agree with me that we come up with a relationship where K is a constant. If the states of the gas change from V1 T1 to V2 T2, then we would also end up with something of this sort. Now, remember in Boyle's law, we dealt with a constant on the right hand side and we made our conclusion. In this method, I'm going to show you how we can instead use the change of state from one to the next and still make the same deduction. That is what we want to apply today. So let's begin by looking at an ideal gas which is in a vessel, just like we had in Boyle's law. So the total number of molecules is capital N, mass per molecule is small m, and then the total volume is V. So we shall get the total mass of the gas in the container, and at the same time we shall get the density. But unlike the other one, I want to introduce something different. Let's try to cross multiply this. When you cross multiply this, you can get that equation for density. I'm doing that for a purpose because when you start from P is equal to a third rho C squared bar, I want to multiply this equation by V. When you multiply this equation by V, you get PV on the left hand side, and the other side you shall have a third rho V, then C squared bar. Now this rho V, you could have seen that is what is here. So we can therefore substitute this one directly to rho V. That is why I was trying to do that. So when we went ahead, we could obtain something of that sort. Now, at this point, we are going to consider the change of states of the gas from stage 1 to stage 2. Okay, so if the temperature changes, we are so sure that the kinetic energy of the molecules of the gas will also change. In that way, that means that this one will change. And remember, we said our average kinetic energy of the molecules of the gas is given by this. So if the temperature changes, then this concept here will change as well. The only thing that is not going to change is the pressure, because Charles tells us that the pressure will remain constant. Okay, so that's why we're saying that suppose the states of the gas change from V1 to V2, then we would be in position to write an equation. For the first state, V1 is equal to a third NM1 C squared bar. Similarly, we shall write for the second one, which will give us the same concept. Now, okay, that is what we know. Okay, if we did divide this equation, that means that the P would disappear and the N would also disappear. You divide this equation with this one, you end up with this expression. You have simplified, the P disappears, the N disappears. Now from this point, we are almost there, but we are left with one concept. Charles does not have mean square speed. Charles has absolute temperature. So we need to introduce the concept of absolute temperature using mean square speed. If you remember, when we're dealing with the Boltzmann's constant, say the kinetic energy is equal to kBT, and this is 2 over 3. So we discover that a half m c squared bar is the rest of the other one. So we have a half mc squared bar is equal to 2 over 3 kbt. Why am I doing this? I want to bring the concept here. This is a constant, Boltzmann's constant. Mass of the molecule remains constant. This half is constant, this one is constant. So the only thing that changes is the c squared bar and the absolute temperature. So in brief, the mean square speed is proportional to the temperature. That therefore means that C1 squared bar will be proportional to T1. And in a similar way, C2 squared bar will be proportional to T2. If that is correct, then our equation simplifies to something which is what Charles tells us, that the change of state will from V1 to V2, T1 to T2, would end up with something like this. Okay, this equation looks a little bit V1 over V2, but you cross multiply and rearrange, you'll get V1 over T1 is equal to V2 over T2. Thanks guys, that's how we go about Charles' law. Now this is an alternative method. You can also use this kind of analysis for Boyle's law, or you could have also brought the analysis we had for Boyle's law in Charles' law, and we still end up with the verification. Thank you.